everybody. Sorry for the delay. The end of the academic semester is always more hell than one can imagine. Do we have a pointer around? Thank you. Okay, it's been a while since I've seen everybody. So let's see. First, a couple of announcements. This is kind of, seems like we have some strange, wonder if let me quickly check to see what the resolution is, because it looks like it's having a hard time matching this. Let's see, is there, what rep rate do we need to be on for this?
Oh, that is better, at least on one side.
On one side it's better. Over here it's all right, but do you have any suggestions for me?
It should be the lowest one, the 60.
Is one of them being retransmitted from California to the... Yeah, there's a delay on the right one. Yeah, what you'd be seeing on the right...
This is the correct rep rate. Is that correct? 60 hertz?
Yes.
Okay, so I think the guy on the left looks good. I'll leave it to you.
The guy on the right is being recoded and sent over.
Okay, so we'll just go forward here. All right, let's see. Quick announcements. So with the scheduling at the end of the semester for me, I've rearranged yet again our schedule. So if you notice here, originally this topic was meant to be next. This lecture is being moved to December 21st. Okay, that's our last week that we had a possible slot here. Next week there will be no class. I'll be up in Los Alamos, actually. There's a meeting of their Quantum Institute. The following week, I believe that's the 14th of December, Richard Hughes will be here to talk about quantum cryptography. And then the 21st, I'll give the final lecture. Okay? So let's see. Last time, I guess Andrew Landau was here talking about quantum algorithms. So I didn't finish this slide, obviously. But I would say there are really, probably you heard about three main algorithms. Maybe you heard parts of at least the three main algorithms. Clearly the most important algorithm that really got this field on fire was Shor's algorithm. The algorithm really at its base is this so-called quantum Fourier transform, which I should say, is an order polylog algorithm in the number of qubits, and that is an exponential speed up over the best known algorithms for doing this kind of order finding, which is at the heart of factoring numbers into their prime constituents. And of course, that's what really got everyone fired up about the field. People are really searching for generalizations of this, and it's really been slow going. I guess you'll have Dave Bacon out here sometime soon, and I'm sure you'll hear from him about the question of the so-called hidden subgroup problem and its generalization to other algorithms in progress that's being made along those fronts. Grover's algorithm is another important algorithm for quantum computation, and it doesn't have an exponential speed up, but just this kind of square root of speed up. It's an provably optimal algorithm for doing database searching in an unstructured database. I would say, though, we're probably the most important thing that will get done in the short to medium term is probably this, quantum simulations. This was really, of course, the original motivator of Feynman for thinking about using quantum mechanics for doing computation, was to solve the Schrodinger equations for many-body quantum systems. And There's, of course, I'm sure many of you are involved in the activities that are going on right now in trying to implement this. How good, it's a question I don't know the answer to. Where does this sit in quantum complexity world, or that is to say, in the world of computational complexity? Is this, it's clearly not an NP-complete problem, but where does it sit? I don't think anyone's addressed that, and it's an interesting question that I think really merits further thought. Okay, so where are we now? Today we're going to talk about the problem of decoherence and errors. Let me start here and we'll go back. I realize my slides are out of order. So far, we've really had a pretty idealized, kindergarten kind of picture of quantum mechanics. And so it's drawn with nice primary colors here. The way we've kind of envisioned the way the world is that we have some kind of perfectly closed quantum system that we can control absolutely perfectly. Now, of course, the real world isn't like that. The real world is much messier. Our control that we're applying to our quantum system is itself going to be noisy and imperfect at some level. And in addition, our quantum system is not some isolated, generally, cannot be perfectly isolated from the outside world. And that outside world has other degrees of freedom that we may not have access to. And we call that outside world the environment. And it's generally itself, in some sense, noisy. And so really we need to start thinking a little bit about quantum mechanics, not as a closed system, but as an open system. Well, okay, so let me move back here. So let's review for a moment what we said was what we're leveraging off of in order to think about doing quantum computations. It was really all about coherent superpositions. So for a qubit, we imagine we have some pure state as a superposition of our classical bit states, 0 and 1. And what was important was the fact that if we were going to do some kind of measurement of some observable, which had some outcome A, we had this rule for calculating the probability of an outcome, which was the square of this complex amplitude. And here it is once again. And when we squared that out, what we saw were these different terms. The first term here, which are the squares of each of these terms, had a perfectly logical kind of interpretation. The probability of measuring something, well, I could get, if the initial state was in 0, there's some probability that it was in 0, and then there's a probability of getting A given that it was in 0. That was this term over here. This is the other conditional probability. And then we had this other stuff, which was the quantum interference terms. And as you see, as I've written it out in these terms, the coefficients in front of here depend upon the relative phase, a well-defined relative phase of these two complex amplitudes. That was truly important in order to have a well-defined interference term over here. That's what we called coherence. Now, when we go through from this this closed quantum system to this open quantum system, what can happen, and we'll talk about this in much more detail through this discussion, is that my well-defined pure quantum state decoheres, goes from something with a well-defined relative phase between those two alternatives to something which I really should think about more like a classical bit that has some probability of being 0 or 1, and no quantum coherence between those alternatives. Okay. Why is that a bad thing? Well, if I have just those two alternatives, I go from a situation where we had those 4 terms, 2 of which in my quantum had my quantum interference, to just a classical set of probabilities and no interference. Okay, so what I've told you sort of at the beginning of this class was a bunch of white lies. I mean, what I said was, first of all, that we should describe quantum states as these vectors in Hilbert space. Well, that was kind of a lie. Really, the most general quantum states are what we call density operators, and we'll spend a little time talking about that next. I said, well, quantum dynamics are these unitary matrices, these unitary maps that take me from one quantum state to another. But in fact, that's a lie too. Really, the most general quantum dynamics isn't unitary at all. It's described by a more complicated mathematical object, which I won't talk about, something called a completely positive map. But if we really wanted to talk about quantum information, we really need to study that in more detail. So this is the introduction. The advanced course will give you that. And the really advanced course will tell you about this, which probably even a lot of you who have, are physicists who have taken graduate courses in quantum mechanics and never even heard about this. We usually talk about a measurement in quantum mechanics as being, well, okay, I do a measurement of an observable. There's a formalism that tells me that those observables are described by Hermitian operators, and those have eigenvalues, and then there are certain orthogonal subspaces associated with those different eigenvalues. And then when I do a measurement, I I collapse the wave function onto one of those subspaces. That's the standard law of quantum mechanics, but that's a lie too. The most general measurements are not like that at all. They're what we call positive operator valued measures, or POVMs. Now, it's a heavy-handed name. We're not going to talk much about this either, but these are just to tell you the real true story of quantum mechanics is underneath here. Okay, so let's talk a little bit about density operators, because if we're going to talk about decoherence, we really need to talk about density operators. So let's return to this picture again. We said, okay, let's imagine I had what I called a pure state, which was this vector in Hilbert space, and we had this expression for the probability of measuring a certain outcome. Here it is, written out once again in those 4 terms. Okay? Now, I can write this in a compact way. This probability can be written as the expectation value of an operator. That operator I'm calling rho. It's called the density operator. Why is it called density? It's anachronistic. It's a vestige of a long time ago, but the name sticks around. In any event, what is this rho? Well, with this rho, if you just look at these 2 expressions right here, it's this operator. Okay? If I take the expectation value, each one of those terms, this one maps to that one maps to that, and these 2 guys map to that. Everyone on with me? So here it is, that operator. Of course, every operator can be written as a matrix. Here it is a matrix, a 2x2 matrix for this qubit, which is just the outer product between this column vector and that row vector. And you remember from way back when we talked about Dirac notation, the column vectors were kets and the row vectors were bras. So here's the density operator. And you notice it has diagonal matrix elements, which are related to the probabilities of the 2 different outcomes. The probability of getting 0 is right here in this matrix element. The probability of getting 1 is sitting right here in this matrix element. So the diagonal matrix elements tell me the probabilities of getting up or down, 0 or 1. What about the off-diagonal matrix elements? Well, they tell us about coherence. Remember back in the previous slide, I said that remember, it was these terms that were responsible for quantum interference. It's these terms that tell me something about the relative phase of 0 versus 1. So it's these terms that tell me something, these off-diagonal matrix elements tell me about the possibility of seeing interference between the two alternatives. Now, here's something that I want you to keep in mind. It doesn't make sense to talk about the off-diagonal matrix elements. It only makes sense to talk about the off-diagonal matrix elements with respect to a basis, right? Because I can do a similarity transformation on a matrix. It's the same matrix, but in a different basis. And those different bases correspond to different measurements I can do. So I can diagonalize this matrix, right? Linear algebra, diagonalize a matrix, Hermitian matrix, I can diagonalize it. That doesn't mean that it doesn't have coherence. It just means it doesn't have coherence in the diagonal basis. It has coherence in another basis, okay?
What does that mean physically?
It means that if I do a measurement in one basis, I will see interference between those alternatives. If I do measurement in another basis, I don't see interference between those alternatives. Okay, so I mean, this is all I did here is I rewrote the same thing in 5 different ways. I haven't told you anything yet about errors or decoherence or anything like that. This is just formalism. It says I can re-represent this pure state as a operator or as a matrix, and I have different interpretation. I have a physical interpretation for what those different matrix elements mean. Okay, but it's still, in this case, a pure state, and that and for a pure state, the density operator is just the outer product of the state with itself. Yes, sir.
Your piece of A is taking A to A, but if I take A to B, is that then the probability of transitioning from A to B?
You mean the matrix element of the density operator? Yes, correct. It doesn't mean the transitioning of it, because that's the kind of dynamical picture of a quantum jump or some transition that happens. What the off-diagonal element between, let's say, A and A prime or A and B would represent how much coherence there is between A and A. Suppose A and A prime were 2 different outcomes of a measurement of the observable capital A. Then I can ask the question, is there interference between A and A prime?
So it's not you have one state and then you measure its probability going into a different state?
No.
Okay.
No. This is not about dynamics. This is about our state of knowledge about the system. And our state of knowledge about the system has different pieces of information. Some of the information we have about it is what is the probability of measuring certain outcomes. The other one is what is the coherence between those different alternatives. That information is encoded in this matrix.
And you can measure that.
Okay, so that's a tricky question. What does it mean to can you measure a quantum state? That's like saying, can I measure a probability distribution? What I can do is reconstruct in the same way that I can say I want to know what's the probability distribution for a 6-sided die. Well, I have to roll the die a number of times, and then from the frequency of outcomes, I deduce, I make some assessment about what's the probability. And similarly, if I wanted to reconstruct the density operator, which is now known as quantum state reconstruction or quantum tomography, what I have to do is I have to have the preparer prepare for me a whole ensemble of states with exactly the same preparation procedure that will prepare this state, for example. And then through a set of measurements, if I have a lot of them, I can reconstruct this. Because if I measure the state, say I ask the state, are you 0 or 1? Well, I'm going to get that answer, 0 or 1. I'm going to get one bit of information. Clearly, there are lots of bits of information in there. Each one of these is a real number. or actually, I'm sorry, a complex number. So that has lots of bits. And I can only do that with lots and lots of measurements. But it's an excellent question. OK, so that was a pure state just rewritten as an operator. So now let's think about how do we go from a pure state to a mixed state? Well, there's lots of different ways, and they're really interesting, in my view, that these very different ways of thinking about going from a pure state to a mixed state all are represented in the same way. So let's say there was some unknown preparation procedure. So I said that the original state was defined by some well-defined preparation procedure. Someone made the qubit with great precision. But say that precision's missing in some way. For example, a spin is generated out of a thermal source. Well, there's some temperature there, and I don't know exactly what the spin is going to be. Or maybe there's, really a preparer, and the preparer's in the black box rolling the dice, and, I'm going to give Deutsch spin up this time, and flips the coin a few times. That would be a kind of ensemble of pure state preparations weighted by some probability of that preparation. Okay? So in that case, whereas any one pure state would be represented by a density operator that's like this, if I have a statistical mixture of pure states, then I would call the density operator like this. Okay? So this state is a state which has a statistical mixture of pure states, not a coherent superposition of pure states, but a statistical mixture of pure states. And if I rewrite now each one of these, say, is a qubit, each one of these has its little density matrix that just like the kind we wrote down in the previous slide. And now I'm going to average over those matrices weighted by a probability distribution. All right? So each one of these matrix elements is averaged. That's what the bar is over them. And when I average that, that could have the effect of washing out these terms. If somehow the averaging over these different alternatives of preparation washed out the relative phase between 0 and 1. And that process of washing out the coherence, washing out the relative phase, is called decoherence. Yes?
I don't know if I can formulate this well enough. If I have a pure state,
Yes.
so I have a dense matrix.
Yep.
If I measure 0, 0, I will get a particular number, won't I? I get the C0 squared.
So I think the thing to keep in mind here is the density operator tells us about something about the probability of outcomes of measurements. Okay? So if I measure, I wish we had a little blackboard here. Oh, there's one over there. So let me quickly.
Okay, I'm sorry. So
No,
that's
no.
the probability of getting together.
Yeah, but there's a point here that I'd like to make. So if I could just. So what we said in a previous slide was the probability of getting some outcome A of some observable is that. Okay?
Without the hat. Right?
This is the operator,
Okay.
and this is the probability of getting an outcome. Okay? So what does that mean as matrix multiplication? Well, this is equal to the matrix, let's say C0 squared, C1 squared, C0, C1 star, C1, C0 star. That's the matrix in between here. Let's put the little bars here because it's averaged over an ensemble. And now I have to multiply so there's A itself is a column vector, right? It's some amount of 0, some amount of 1. So I'll call that alpha and beta. And here, this is the bra. The bra is the Hermitian conjugate. So now I have to do out matrix multiplication. I'm not going to do that because it's a pain in the butt. But you could see that all four of these terms are going to contribute to the probability of getting that outcome. If alpha were, say, 1 and beta were 0, that's the case of asking what's the probability of getting logical 0. If beta was 1 and alpha was 0, that's asking me the probability of getting 1. If alpha is 1 over root 2 and beta is minus 1 over root 2, for example, then that's asking me what's the probability of getting the state minus, which you remember we called 0 minus 1 over root 2. So I can ask the question, what is the probability of getting anything? And that's how I do it. But generally, all four of these things come into play in that. Yes?
Are these just the simple measurements, or are these POVMs?
I mean, so an orthogonal measurement versus POVM will ask me a question. Yeah, in this particular case, I guess these are simple measurements because, well, for the aficionados like yourselves, who's sitting in Carl Caves' class, I could also write this in this way. It's the trace of rho with that projector. So my particular measurement is an orthogonal projector rather than a general POVM. But generally, I would replace this with a POVM element. Okay. Yes.
Pursuing this some more.
Please.
So now I understand that to be the case where you're back, where you're not doing a mixed state.
No, this is good. This is a mixed state sitting right in here. It's a mixed state. So the mixed state itself is a density matrix. Every state is a density matrix. Some are pure, some are mixed. But every state's a density matrix.
So if I had a pure state,
Yep.
and I had 1, 0 again, trying to measure 0, probability getting 0.
Yep.
That's the probability getting 0 of
So
the
that-
pure state, right? C0 star.
Well, okay, indeed. So if this were if I were asking the question, what's the probability of getting probability of getting 0, that is C0 squared. Whether the state is pure or mixed, that's always true. Now, if I ask the question, let's do out an example, because I think it's useful. Maybe I should do out the multiplication. Let's do the example of what is the probability of getting minus? OK, let's do that. So that's going to be 1/2, 1 minus 1, C0 squared, averaged over the ensemble, C1 star, averaged over the ensemble, blah, blah, blah. OK, I just factored out my 1 over root 2. That's where that half came from. OK, let's do it. So that's 1/2 of 1 minus 1. And then I have C0 squared minus C1 star bar. And then in the other column, I have C1 C0 minus C1 squared. So now I'm going to multiply that out, and I get
C0 squared, C1 squared, minus the
right, exactly. So I get this plus C1 squared, and then the minus this guy. I can't, it's hard for me to do this on the fly. on the board here to check all my signs. Let's see, I get the signs right? Help me out here.
There's a plus in the last one should be plus.
Yeah, that's right. Okay, so that's the answer. So what that says is, now, what would be the difference if this was a pure state versus a mixed state? The question is whether or not, say, these off-diagonal terms are 0 or not. If I had a pure state psi, which was C0 alpha plus C1, 0 and 1, if that was my pure state, and these were two non-zero coefficients, then I have all terms. Whereas if this was a mixed state with the same probability of 0 and 1, but no coherence between 0 and 1, then these two terms would survive, but these terms would be gone.
Does mixing always reduce?
No. Yes?
If somebody shows you a density matrix, can you tell if it's pure or mixed?
Good question, yes. You can do that by the following fact. So, the trace of a matrix is the sum of its diagonal elements. Okay? So the trace of rho is equal to the sum of this plus this. What is that? That's always 1. Always. Whether it's pure or mixed, it's always true, because that's the sum of the probability of getting 0 or 1. However, what's the trace of rho squared? This is 1 for pure state and less than 1 for a mixed state. So that's the litmus test. The litmus test. You know, does the paper turn yellow or blue? It's taking the trace of rho squared.
So you can actually increase coherence by mixing at times?
Uh,
Or no?
Oh, no, you can keep it the same. It will always stay the same or decrease. Now, you can purify in other cases, but not by mixing. You'd have to do some other more complicated to try to purify a system. So that's what we call it. We've reduced the purity or increased the purity. Excellent. Okay. Now, there's a kind of related way that I could reduce coherence. What I just said there was, some, demon inside the black box was flipping a coin, or something came out of a thermal source with an unknown quantum state, and I just had to wait. Okay, it could, I have a Boltzmann distribution of pure states, and I just weight them. There's another way that you can imagine a mixed state arising, and that's, what we have assumed in our ideal world was that we were controlling the quantum system in some way by applying some set of control pulses that were very well defined and took the quantum system through some well-defined dynamics. So mathematically what we say is there's some Hamiltonian that governs the dynamics, and it is parameterized by some parameters that are functions of time. The electric field goes on, the electric field goes off. The RF pulse is well defined. Well, of course, that's not perfectly true. There's always noise. And what that means is that I don't really know exactly what the time sequence is of the electric field. It has some distribution of amplitudes or phases of the controls. And what that means is I really need to weight again. So this would be the pure state for a given lambda, but I don't know what lambda is exactly because there's noise on my lambda. And so when I average over that, I get a mixed state. Now, just some jargon so that you can touch base with the literature if you ever read it. Typically, in those kinds of processes, depending on the nature of the noise and so forth, what one can see is this kind of an exponential decay of these different matrix elements. And those exponential decays have associated rates of decay or time constants associated with those decays. And we call those, the rate of decay of the population, we call that time constant T1. And the rate of decay of the off-diagonal elements, which has to do with the rate of decay of the coherence in the system, that time constant we call T2. That's a language that comes out of NMR. Yeah.
So your trace is always 1.
The trace is always 1.
So how can the diagonal elements decay that much?
No, they can't. What can happen is they can decay so that they go the population difference,
They can oscillate or something.
or they can go to an equilibrium value, right? Suppose I have, it could be the case that I always decays to the ground state. So say 1 is the excited state and 0 is the ground state. Or I might have some finite temperature. So it always goes to a Boltzmann distribution, for example. Okay, so, but there's yet another and quite interesting, in my view, that this really is the same thing. Another way we can get a mixed state, starting from a pure state. And that has to do with the environment, and the environment itself being a quantum object. And the environment itself then can interact with the qubits, which we call the system, and thereby become quantum correlated with the system, and thereby become entangled with the system. Okay, so let's think then about entanglement, because when we talked about entanglement, this was something I completely sloughed over, but a truly, truly important point, maybe the most important aspect of entanglement. So let's go back and just think about bipartite, two systems, two parts, entanglement. So here's a state that's describing Alice and Bob. They are given some qubits, each one a qubit, and there's some state that they jointly assign to the system. Now, according to the rules of quantum mechanics, they can each do a measurement, say, on their qubit, and in whatever basis they like, and they can ask about the joint probability distribution. What's the probability for Alice and Bob, for Alice to get result I and Bob to get result J? Well, there it is. I mean, that's quantum mechanics, right? That again, we're always talking about simple measurements here. The outcome Ij is there some eigenvector of some observable that corresponds to Ij, and you take the inner product between the joint state and that eigenvector and you square it. Okay? So that's how we generate from the quantum state the joint probability distributions for measurements of Alice and Bob. Now we can ask just a purely, statistics question. Given a joint probability distribution, what are what we call the marginal probability distributions? What are the probabilities of Alice to get some results, irrespective of what the heck Bob is doing? And what's the probability for Bob to get some results, irrespective of what Alice is doing? Well, we just, sorry, this got overlapped here. We sum over all, to get Alice's marginal probability distribution, we sum over all of Bob's possible results. And to get the marginal for Bob, we sum over all of Alice's. That's statistics. So now I ask you the question, what is the quantum state for Alice? I mean, Alice is making measurements, so Alice should be able to predict the outcomes of her measurements by a quantum state that she assigns just to hers. She should be able to do that without knowing what Bob's doing. Similarly for Bob, he's going to get some results, and he wants, I mean, if quantum mechanics says anything, it predicts the probabilities for outcomes of measurements. So I ask you, what is the state of Alice's qubit? And what is the state of Bob's qubit? Well, let's look at a specific case where Alice and Bob share a Bell state. Here it is. Remember this one? So we could do, ask the questions about first of all, here are the joint probability distributions for measurements in the logical basis. So if the probability for Alice and Bob to both get 0 or both get 1 is a half, and the probability for one to get 0 and the other to get 1, that's impossible in this state, right? Okay, so now I can calculate the marginal probability distributions just according to usual rules. I sum over all of Bob's results for Alice. So what that tells me is that the probability for Alice to get either 0 or 1, she has a 50-50 chance of doing that. Same for Bob. So from that, I at least know that their density operators have this form, right? On the diagonals, they have a half, because we said on the diagonal tells me the probabilities of their outcomes. But what about the off-diagonal matrix elements? What are they? Well, to figure that out, we have to think about interference between results. So we have to think about other bases. So let's ask the question, suppose Alice, instead of measuring in the logical basis of 0 and 1, suppose that Bob decided to measure in the basis of eigenstates of x. It's back when we talk about photons, these are like plus or minus 45 diagonal. So that this is that orthogonal basis. Well, I could do the same thing that we did before. Ask about, first of all, what's the joint probability distributions? Here they are. The probability for them both to get plus or both to get minus is a half, and it's impossible for one to get plus and one to get minus. That follows directly from this entangled state. So from that, it follows, again, that the probability of Alice to get plus or minus is 50-50 chance. The probability for Bob to get plus or minus is also 50-50 chance. And that's true no matter what basis I choose. And there's only one way that can be true. If this is a completely mixed state with no off-diagonal matrix element. There's no other way that no matter what basis I look in, because back there I said, when we did this, it depended, well, I guess I erased it. Oh, here it is, this thing up here. What was going on in this part of the matrix, how that all interfered in different bases, it would look different. The only way that could never look different, no matter what basis, is if it's the identity matrix or some multiple thereof. And that's this. So that's a truly fascinating result in my view. What it says is that I have a pure entangled state of a joint system. And I ask the question, what state should I assign to the subsystems? They have to be completely mixed. That's a unique property of quantum mechanics. It says I have the complete description of the whole, but complete ignorance of the parts. The parts are completely random, whereas the sum is as unrandom as quantum mechanics allows. How can that possibly be? Well, I don't know, but that's the way life is, or the world, or whatever you want to call it, our intelligent design. It's the way in which it's happened, that somehow in the microscopic world, there are states of the system for which we can have the maximum description of the whole and absolutely know nothing about the parts. So what that what is the implication of that? I mean, that has, of course, implications for all kinds of things. But in the context of today's lecture, the problem of decoherence, what that says is that entanglement of the system degrees of freedom with the environment leads to decoherence of the system. If the system becomes quantum correlated with anything else, you're in deep doo-doo. Because the system, in some sense, has been measured by the environment. And we know measurement's a bad thing, sort of. I mean, it can destroy a quantum system. Because when you measure it, it collapses a wave function. Now, it's not quite a measurement. Here's another way of looking at it, and I think a useful picture to keep in your mind. Let's suppose that I had this system was initially in the state plus, 0 plus 1. Suppose through some interaction with the environment, the system environment, say the environment was 1 qubit that we didn't know about. It's hiding out there somewhere. And suppose that the system environment joint system became quantum correlated in this way. What that means is that the system qubit has been decohered to a completely random qubit. Why? Because the environment holds a record of what state the system is in. If we were to measure the environment and find the environment is in 0, we know the system is in 0. If we were to measure the environment qubit and find it in 1, we'd know that even if we don't look at the environment, the fact that the environment's out there and has been correlated with the system in this way decoheres the system. A measurement happens when we actually look at this. So this is not quite a measurement. It's decoherence. And so it's an important picture to keep in your mind. Quantum interference occurs when the two alternatives are in principle indistinguishable. If they are in principle distinguishable, you've lost interference. And this state, in principle, distinguishes between 0 and 1 because that information is stored in the environment, even if we don't look at the environment. Yes, sir?
Once the environment forgets, is the coherence restored?
Well, if the environment, if the dynamics were such that the environment lost this record, and that would have to happen in a coherent way, then yes. So if you can, and that's what's called a quantum eraser. If you can erase that information, then you can regain the coherence. And in fact, well, that's a foreshadowing of error correction. Okay. So this point that a quantum system, when interacting with the environment, can become entangled with the environment, in some sense answers the question, where are the Schrodinger cats? Remember Schrodinger's cat paradox, that I can have this state of two macroscopically distinguishable alternatives. The cat's alive or the cat's dead. But that was somehow caused by a quantum superposition of a nucleus decaying or not decaying. Where is that coherent superposition of the alive and dead cat? Well, the answer is it quickly decoheres into either the cat's alive or the cat's dead, because it's very, very easy to decohere that circumstance. Here's a kind of toy model of that. Here's let's imagine the quantum state of 4 qubits. that is created by this quantum circuit. Okay? It has these controlled knots which entangle the different qubits together. And if you go through the algebra, it's pretty simple to show that this is true. In fact, if I added more lines here and more controlled knots from the first qubit, I would just get more 0, 0, 0, 0, 0, plus 1, 1, 1, 1, 1, 1, 1. What does this represent? All the spins up, n of them, in this case 4, or all the spins down. Let's suppose I had an Avogadro's number of them. Okay? Is that a delicate state? You bet it is. Why? It just takes one interaction, which is one of those qubits with the environment, and you're dead. Or alive, exactly. Very good. And so you can show, this is a good little exercise. Let's suppose that, so here's in my particular example here, I had 4 qubits as my system. Let's suppose just one of them comes in and interacts with the system in such a way that the equivalent interaction of the system with that one environmental qubit is like a controlled knot between the system qubit and the environmental qubit. And then I throw it away. I don't know anything about that environment because the environment's just out there and I can't.
You mean measured? Forget the
No.
answer?
You could think about it that way, or you just throw it away. You just it's the same thing. Either measuring and throwing away the answer, or just throwing away the qubit is equivalent. So I'm going to put that qubit in the trash. Another way of saying is I just have no access to this qubit. I don't even know it's out there. My lovely superposition of all ups and all downs is now this mundane. Either they're all up or they're all down. There's no coherence between those two alternatives. Okay, so what is the implication of all of this for quantum information? So remember, all our quantum algorithms at some sense rely on quantum parallelism. They rely on the interference between alternatives. And we just said that decoherence through all these different paths, either poor initial preparation, it's not really decoherence, that's just poor initial preparation, bad controls that are noisy in some way, not perfect in the way that you thought they were, or just other degrees of freedom that happen to couple to your nice degrees of freedom that you want to call your qubits, can cause decoherence, and thus can destroy the interference between the computational paths. That's errors. And moreover, this is something that I didn't prove or even discuss, but I'll mention now, which is that in a lot of circumstances, the rate at which this happens, those T2 times, for example, can be much, much faster as the number of qubits grows, if you're not careful. Now, when quantum computing was first being contemplated, in fact, when Shor's algorithm first was published, there was this famous paper published by Serge Haroche out at the Quantum Model in Paris called Quantum Computing Dream or Nightmare. Because if you look at this, it's clearly, if this is what we're stuck with, we're really doomed. If there's no way to counteract decoherence, any gain that we get in quantum parallelism is quickly reduced by decoherence. So we're never gonna, we're not gonna be able to fight this. It seems impossible. I mean, errors can happen, of course, to classical bits too, but there are methods that have been developed to deal with that. First of all, of course, the main reason for dealing with digital computation as opposed to analog computers is that you can error correct. That is to say, first of all, if you encode not in a continuum of states, but in a discrete set of states, then you are robust to noise. You know, if I have a transistor, there's a certain threshold before I call the 0 or 1. So if I can maintain the noise below that threshold, then I'm going to have a pretty robust bit. Of course, errors might happen, but then in principle, I can try to still keep the data uncorrupted through the process of redundant encoding. So a simple way I could say of dealing with errors of the bit flip kind that say take 0 to 1, 1 to 0 is the following. Let me encode a so-called logical 0 as the state of 3 bits. This is classical bits, okay? I'm not talking about quantum bits here. So 3 transistors in the 0 state and is going to be called the logical 0, and 3 transistors in the 1 state are going to be called the logical 1. Every other state is an error, is not a real state. So let's suppose that there's some small probability p for one of the bits to flip. What happens to my states, my registers in my computer? Well, the logical state 0, if there's an error, will go to one of these 3 states if one of the bits flip. And the logical state 1 will go to one of these 3 states. But these alternatives are still distinguishable. All I have to ask the question is, all you have to do is majority voting. And majority wins, minority loses. If more than, if 2 or more of my bits are 0, I call it 0. If 2 or more of my bits are 1, I call it 1. And so all I have to do is do majority voting. I ask all 3 bits, what are you? I say, oh, OK, in this case, clearly the 3rd bit flipped. So I just flip it back. Now, of course, this only works if the probability of having 2 bit flips is small. Otherwise, 0 could go to one of these states. So if the probability, and you can just show that if the probability of this happening is less than a half, then this is robust. I can always keep my data without losing it to bit flip errors. Okay, so that's classical error correction. That doesn't bode very well for the possibility of doing quantum error correction. I mean, first of all, is a quantum computer an analog computer or a digital computer? Well, I don't know. I mean, the quantum state is encoded in this qubit, which has these complex numbers, which are continuous variables. Sounds pretty analog to me. I mean, any small change in the relative phase or relative amplitude of alpha and beta changes the state, and that's a continual process. That sounds pretty bad. We wanted to make our quantum information redundant. So it sounds like the first thing we would like to be able to do is to make lots of copies of my qubits. So take my quantum state psi and make 3 copies of it. Can't do that. We'll talk about this in a moment. There's the so-called no cloning theorem, which I haven't proven, but I'll show you in a moment. And it just gets worse. I mean, so what did we want to do in classical error correction? We wanted to ask the 3 bits, are you 0 or 1, and then poll them and see who is the majority. And then, but if I ask this 2-bit, are you 0 or 1, forget it. I've just collapsed the state. I've lost all the power of the quantum computation. So how in the world am I going to ask my quantum bit what its state is? Well, I'm dating myself here, but the answer to the first question is it's both. It's analog and it's digital. In the same way that a quantum particle is both a wave, or a quanta is both a wave and a particle, a quantum computer in some sense is both analog and digital. And perhaps in some sense that's where its power derives from. It's analog, as we said, in the sense that the two complex amplitudes that define a quantum state are continuous variables. But it's digital in the sense that when I measure it, I find 0 or I find 1. I don't find the cat in limbo. Okay? Now, what's amazing about that is that if I do things properly, and we won't have much time to talk about that because that's a pretty sophisticated topic, but although the errors in principle can move the qubit through a continuum of states on the Bloch sphere, for example, I can discretize those errors. I can force those errors into a discrete set that cover all possible errors that can happen. And in doing so, then make this, at least at this level, the power of digital encoding, the power to sweep entropy away without destroying the state. What about this cloning business? What do we mean by cloning? Well, cloning would be the following thing. What we seek is the following kind of transformation. A cloning transformation would be take an arbitrary state of, say, a qubit. It doesn't have to be a qubit, but let's just stick to that for concreteness. And let's say I start with some fiducial state. This is my blank sheet of paper. Let's call it 0. And what I would like to be able to do is some kind of quantum dynamics which takes me from this to this. That's cloning. That's not possible for an arbitrary state psi. Why? Well, if it's possible for an arbitrary state psi, then it's got to be possible for a superposition of states. And any quantum dynamic is a linear map. Anyone. Always. Quantum mechanics is linear. So what that means is, so let's suppose that psi were written as a superposition of two states, psi 1 and psi 2, with some amplitudes. And let's apply this transformation to this state. Well, here it is. Here's the state psi, which I've written out now as a superposition of either psi 1 with the fiducial state or psi 2 with the fiducial state. And when I do now the mythical cloning operation, the first part of superposition goes to psi 1. And the second part of the superposition goes to psi 2. But that's not what I wanted. What I wanted was psi times psi. And that's going to have cross terms in it. And they're not there. So linearity of quantum mechanics forbids me from doing this for an arbitrary state. Cannot clone an arbitrary state. Now, that doesn't mean that I can't copy specific states. I can copy states if they are orthogonal. If they're orthogonal, I can copy them with perfect fidelity. That's just classical copying. Classical distinguishable states are orthogonal states in the quantum language. So for example, let's say I just wanted to copy 0 or 1. Okay? Those are two orthogonal states in Hilbert space. So here's the map. I want to take my fiducial state will be 0. I want to copy into the fiducial state either 0 or 1. So I'm going to do this map. If the initial state is 0, 0, I'll leave it alone. If the initial state is 1, 0, I'll change it to 1, 1. Is there a quantum operation, a quantum dynamic that does that? Yeah, that's the controlled knot. So that's allowed. But what it does to the state psi is this. It doesn't create psi times psi. It creates this entangled state of the two qubits. Okay. However, that might be good enough for the quantum analog of error correction. Let's try to do a bit. Let's say that there's some kind of bizarre error that happens in our system that can flip a bit. With some probability, the state psi goes to this state. That's a bit flip error. Takes 0 to 1 and 1 to 0. With some probability, my state flips, decoheres in this way. Can I correct that error? And the answer is yes.
Does that error actually happen?
It certainly will as part of a more general error, and we'll talk about that in the very last slide. But let's just for the moment ask, could we correct such a thing if that was the only thing that were to happen? Only error. That doesn't happen, okay? But let's just imagine that that happened. Let's just think, does quantum mechanics allow me to deal with that? The classical kind of error flip? 0 and 1 bit flip. So I'm going to, just like before, define logical qubits rather than physical qubits. In this case, I have 3 physical qubits, and I'm going to encode a logical state 0 as all 3 qubits in 0. And I'm going to encode a logical 1 as all 3 qubits in 1. Okay? So that defines a 2-dimensional Hilbert space in this much 8-dimensional larger space, right? Because there are 3 qubits. Each qubit has 2 states. So for the 3 qubit, the Hilbert space is 8-dimensional. And I'm picking out 2 orthogonal states in that 8-dimensional space. And I'm going to look at every superposition of these 2. How do I encode the state? Well, here's a quantum encoding that takes the physical qubit and encodes it into 3 qubits in a logical space. Here is the circuit that does it. So here's my initial physical qubit, and now I have 2 other qubits that are in my fiducial state, and I do this copying operation through the controlled knot. Now it doesn't create psi times psi times psi. What instead it creates is an encoded version of psi, which is a superposition of the logical 0 and the logical 1. All right? So what good is that? Here is the key. Measure the error, not the data. If we measured the data, if I asked each qubit, are you 0 or are you 1, and did the majority polling, we just said that wouldn't work because we would destroy it. But that's not what we need to do. We need to just ask you, are 2 of you the same? Or, are you different? Can I do that? Can I ask that question without measuring an individual qubit? And the answer is I can. I can because I can measure a joint property of the system rather than the property of the individual qubits. And that joint property is going to be measuring a product operator. I'm going to ask qubits number I and number j, what is your value of the observable z? Okay, I'm not going to ask the individual qubit I and the individual qubit j. I'm going to ask the 2 qubit ij, what is the product of your z? We'll find out in a moment, how can I ask 2 qubits a question without asking any 1 qubit a question? That's key. Now, these operators have eigenvalues, and those eigenvalues are +1 or -1. And it's +1 if both qubits have the same parity, that is, say they're both 0 or they're both 1, and it's a -1 if they're different. So I measure. I'm going to measure 2 observables. I'm going to measure the observables z1, z2, and the observable Z2, Z3. I can measure both of those observables without destroying the state because, in a compatible way because they commute, right? We have to have commuting matrices, commuting operators. That's one of the rules of quantum mechanics. Can I ask the question of these two? And I'm going to get either +1 or -1 for each one of these joint observables. And here are the possible so-called syndromes that can happen. Either I get +1 and +1, in which case nothing happened, and I do nothing. If I get a +1 -1, it means that 3 was different. So I flip 3. I don't know what 3 was. I just know it's different from the others. You got it? Isn't that cool? So I don't have to know what the value of any qubit is. I just have to know what its relationship is to the others. And I can measure that relationship without measuring the individuals. How do I do that? Well, here's a circuit that does that. Homework assignment? Professors love to give out homework. Clark, you remember that. What?
Comparing the state and then measuring it. So the first 2 days are what we had before.
That's right. So here is the encoding right here. Now I want to decoherence happens maybe, and that decoherence is only in the form of bit flips. It's that weirdo error, but let's just imagine that that's the case. Now I'm going to do what's called syndrome diagnosis. Here's one part. I have to do 2 measurements. I have to measure the joint operator Z1, Z2, and I have to measure the joint operator Z2, Z3. So here's just an example of how I would measure the joint operator Z1, Z2. What I do is I bring in, that only gives me 1 bit of information, right? +1 or -1. So I need 1 qubit to make that joint measurement. So I bring it along. It's called my ancilla. And I do a entangling operation between the ancilla and the first bit and another entangling operation between the second qubit and the ancilla. I claim that the value of that measurement, +1 or -1, is the value of, will come out to be a measurement of the joint Z1, Z2 observable of these 2 qubits.
And if I measure it, it doesn't mess up the other 2?
No. What it does is it projects the system onto the 2-dimensional subspace of the 8-dimensional space in which that error happened. So I can have a superposition of nothing happened or bit flip 1 happened. If that were the case, which is a possible quantum dynamic, then this qubit will be in a superposition of +1 and -1. With probability +1, nothing happened. With probability -1, say 1 flipped. And when I do the measurement, the state then just gets projected onto that part of the universe where, say, bit flip 1 happened. And now that I know it, I apply the X operator to qubit 1. And that maps it back from that 2-dimensional subspace back to the logical subspace. Isn't that cool? Yeah. Now, coming to the question that was raised earlier, that's clearly not the only error that can happen. Here's another kind of error that has no classical analog. Let's suppose that there's what we call a phase flip error. So not the bit didn't flip, but just the sign of the phase between 0 and 1 flipped. Again, it's not reasonable to think that that would be the only error that can happen, but it's a kind of error that could happen, and if it did, we need to be able to recover from it somehow. Now, that, it turns out, is equivalent to a bit flip, but in a different basis. It's equivalent to bit flipping, but in the basis plus and minus. You remember the plus and minus basis. That's the x basis. So all I have to do, if this was the only error that happened, is encode, but encode in this. And here's the encoding circuit that does it. And here's the syndrome diagnosis that does it. OK. Now, here's something that if we had more time, which we clearly don't because I'm already over time, is an important fact and kind of surprising. An arbitrary error on a single qubit can be probabilistically either a bit flip happened or a phase flip happened or both. An X error, a Y error, or a Z error. Yes?
It's not just like, the block sphere is pointing up here and now it shifts over a few degrees. That doesn't happen?
It does, but that is a statistical mixture of one of these three things happen. And when I measure which one of those things happens, I project onto it. That's why I was saying it's both analog and digital. I can, even though there's a continuum of motion, it's a superposition of an X error happened entangled with the environment, or a Y error happened entangled with the environment, or a Z error happened entangled with the environment, or nothing happened entangled with the environment. And when I do, and Peter Shore, lightning strikes twice, discovered this fact.
Strikes more often the smarter you are.
I guess there's some correlation there, but this is pretty darn smart. Came up with the first idea of quantum error correction and showed, this was really was, for those of us like myself who have been thinking about quantum mechanics for many years, the whole idea of quantum error correction, I think, was the most important realization that's just changed our whole mindset. The idea that decoherence can be, in some sense, discretized and removed is just, no one believes it. That's why Serge Haroche said, forget it. Serge Haroche is, this close to Nobel Prize. He's a smart guy. But here's an example of a error correcting code, which we won't describe, but it's the same basic idea. It's a 9-qubit code. What you see what it is, each one of them, remember we had like plus, 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 or 0, 0, 0. Now this is some combination of the two, right? It's each, I have 3 blocks of qubits, and each block itself is 3 qubits. So it's kind of encoded and encoded, and it's turtles all the way down. So just 2 more slides to conclude. Number 1, the general idea, the way quantum error correction works is I define a logical subspace of a bigger dimensional Hilbert space. So the redundancy is still there, just like in classical error correction. I need to have redundancy. The redundancy is in Hilbert space. I have many more states than I need if there were no errors, but I need those extra states to account for errors. The errors, the way in which the encoding has to work is that those errors have to map the logical space to an orthogonal subspace so I can distinguish the errors without destroying the system. And what I have to do is I have to measure which subspace it goes to with and not the state that it's in. Another way of looking at this is the following, and I think that this is from a more of a physicist's perspective. What we're making use of is the fact that we're distributing the quantum information between different physical objects. And those physical objects might be distributed in space. So it's in the information is in the entangled state. not in the individual states of the qubits. The individual qubits have no information. Because what we said is if I looked at the state of an individual qubit, it was random. The information's in the joint state. And the environment can't learn about it because the environment acts locally. So encode globally, not locally. It's the anti-Walmart slogan or something. Okay, I'll just conclude here with what's the last ingredient here that we don't have time to discuss in our introduction, but you can go off and learn more about it. So far, what I really did is I just accounted for, the quantum state could decohere through these mechanisms. But there's other bad things that can happen. When we apply a quantum gate, for example, we may not do it perfectly. For example, we had a rotation on the Bloch sphere. What if we rotated not by pi, but pi plus 0.00001? That's just a slight over rotation. For sure, we're going to do that. Turns out that, in principle, I can deal with that. Moreover, I'm going to have to diagnose the error and then recover. I'm not going to do those things perfectly. So I have to be what's called fault tolerant. And through encoding, in encodings, in encodings, in encodings, in principle, one can make a circumstance that is fault tolerance as long as the errors don't happen too much. Because the extra encoding means I have to do more error correction, more stuff. So if I'm just going to start accumulating more errors. Turns out that there's a kind of threshold. And this is a very important result, that if the error probability per qubit is sufficiently small, and what sufficiently small is unclear right now, then in principle, one can perform computation forever.
So you want to say p is less than 10 to the minus?
I do. I'm sorry. That's what I would say.
That's false.
Now, where does this number 10 to the minus 4 come from? I mean, for a decade almost now, I guess not a decade, more like 8 years, people have, the threshold was first proven, I think it was proven, or at least prove the existence of a threshold, not the value of the threshold, by John Preskill and his students, Van Gottesman. I believe they were the first, but I'm not sure about that. It could have been I think it was maybe simultaneously done at Lano, Manny Knill, and their group and others. But in any event, the existence of a threshold was proven in 1997. What its value was, not clear. We're still trying to find that goalpost. The existence of a threshold is extremely important. It says that in principle, if you can control your system well enough, then in principle, you can have universal quantum computation with arbitrary numbers of qubits. Now, if the number really is 10 to the minus 4, I think we're in trouble. Are we really going to be able to control everything so that the fidelity of every operation, is got 4 nines in it, less than a thousandth of a percent error in any operation? I'm not an experimentalist, but I wouldn't wish that on anybody. We're still thinking about this problem, we meaning the broader community, about how one can more cleverly encode and under what circumstances can you improve this threshold. And I think it's an open question. But just the existence of a threshold is an extremely important result. Okay, I'll conclude there. So next week, no class. 2 weeks, Richard Hughes, and then one last lecture from me.
So I have a question about your discrete set of gates here.
Yep.
Does that mean that your error correction code depends upon your gate set?
Yes.
If you had gates that rotated by 9 degrees, you could do it. But if you had a gate that rotated by 13.5 degrees, you require...
You couldn't do it fault tolerant.
unless you had code that understood 13.5 rotations.
Indeed. I mean, the code, that is correct. So generally, I mean, I need to be able to do an arbitrary rotation, but I generally do that through a series of rotations, 90 degrees in this direction, 45 degrees in another direction.
And then 22 and a half, and then
So, but I have maybe I have only 2 gates through a series of them.
Okay.
But I need that, and my code needs to understand that that's what I'm using.
okay, cool. Thank you very much.